Welcome back to Calculus 3. I'm Dr. Jeff Groh. You may be wondering, this is a Calculus 3 course. To this point, we've not done any calculus. All we've done is algebra. Today, we're going to continue in that vein, but I promise you, we will have a lot of calculus coming. We're going to speak first of cylinders and quadric surfaces. Now, you might think you know what a cylinder is, but we have a specialized definition in this course. To explain the definition of a cylinder, let me draw a picture first. Suppose we have a plane and a curve on that plane. This curve doesn't need to be a closed curve. It could be open, it could be closed. But then we have a line that intersects the plane at one point. The curve is called the generating curve. The line, if we take parallel lines that intersect the curve, we can think of sweeping these along a path generating a surface. The set of all points on these lines is the cylinder. Each of the lines that intersects the generating curve is called a ruling. Many of you may have had something like this in mind when I mentioned cylinder. This is called a right circular cylinder, in the sense that the generating curve is a circle and the rulings are at a right angle to the plane containing that circle. Let's see a plane curve in R3. And let L be a line intersecting the plane at one point. So we're not assuming the line is permitted to be inside the plane. The set of points on parallel lines to L that intersect C is called a cylinder. C is called the generating curve. The lines intersecting L are called rulings. Let's suppose that we are in R3 and we have the equation x squared plus y squared equals 9. This equation does not constrain z at all. Labeling the positive x, y, and z axes, which is customary, we can see that we'll get a circle of radius 3 down in the xy plane. But z is completely unconstrained. If we sweep this circle up and down, every point that we sweep through will be on this cylinder. This will be a right circular cylinder. As another example, suppose I'm in R3 again, and the equation I give you is y equals x squared. This too is a cylinder. In the xy plane we'll have a parabola, but that will be swept vertically. A cylinder, a parabolic cylinder, but still a cylinder. A cylinder is an example of what is called a developable surface. A developable surface can be constructed by sweeping a line in space. Since cylinders are constructed by sweeping parallel lines to the line L around some generating curve C, every cylinder is a developable surface, but not every developable surface is a cylinder. An example would be a cone. Here we're sweeping the line not parallel, but with a gyrating motion, and that generates the cone. Each point on the cone is on some line that lies in the cone. So is something called a hyperboloid of one sheet. They have these rulings that go around, and there you're not just gyrating, you're also moving along a circle while gyrating in order to generate the hyperboloid of one sheet. We'll talk more about these later. As yet another example, suppose we have z equals the sine of x. Y is now unconstrained, so we'll take whatever curve we get, the sine curve, in the xz plane and sweep it along the y-axis in order to generate the surface. You can see that on the xz plane you generate a sine curve, and you'll continue that in both directions, generating what looks like, I don't know if you can see this, a corrugated sheet of metal, more or less. Looks like a corrugated sheet. As you can see, cylinders can be constructed by bending a sheet of paper around that generating curve. In that way, from the internal perspective of a creature whose entire universe is a cylinder, their space is flat. It can be unscrolled and flattened out. Any triangle that you draw on the flat sheet of paper and scrolled up into the cylinder is still a triangle from the perspective of a person constrained to move around, only within the surface. They too would have the same geometry as in the plane. They couldn't distinguish their universe from a flat plane. We're now going to talk about quadric surfaces, but first I would like to recall to your memory your old conic sections. You might recall that conic sections solve equations of the form ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. And you can even discover what kind of conic section it is by looking at b squared minus 4ac. If this is negative, then you're dealing with an ellipse. If it is equal to 0, you have a parabola. And if it's greater than 0, your conic is a hyperbola. The generalization to R3 is the class of quadric surfaces. They solve equations of the form 0 equals ax squared plus by squared plus c z squared plus dxy plus exz and blah blah blah. No more than quadratic terms. All terms after these quadratic terms will end up being linear terms or constants. Those are quadric surfaces. And we are going to pick out 6 different kinds and classify those. And we are going to classify 6 different kinds. First, consider quadrics of the form x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. If you were to cross out, say, the z squared over c squared term and just look at xy's in the plane, what you would have would be an ellipse. In fact, in each planar cross-section, let's suppose we eliminate the z for a moment, we will get an ellipse in the xy plane. But if you eliminate the x, you get an ellipse in the yz plane as well. And if you eliminate the y in the xz plane, you also get an ellipse. You get something rather football-shaped, or perhaps even tic-tac shaped would be one possibility, but even better, how about something like a Mentos, a type of candy which has cross-section which looks something like this. Yeah, it can be squished on the side. It doesn't have to be like a football. It doesn't have to be circular around. It can be squished like a flattened football. You'll remember that if you have an equation of this form, the larger of the two is the semi-major axis among A and B, and the smaller will be the semi-minor axis, semi meaning half. So for example, suppose we have x squared over 16 plus y squared over 25 plus z squared over, let's say, 4 equals 1. This is an ellipsoid. How do we graph it? We'll go 4 units in both directions on the x-axis. On the y-axis, we'll go 5 units. So far, that gives us an ellipse in the xy plane. On the z-axis, we go 2 units. So you can see what this might look like. Something like this. Kind of a squashed ellipsoid. So all of these are going to be oids when we're dealing with these quadric surfaces in R3. The second class is the hyperboloid of one sheet. We're going to look at x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Can you see the difference between the hyperboloid of one sheet and the ellipsoid? We have a minus. Now, it doesn't particularly matter where that minus goes. It can go in front of the x, in front of the y, or in front of the z, but there should be one and only one minus sign when you're equal to positive 1 on the right-hand side. Then you get a hyperboloid of one sheet. The idea being that, for instance, if you hold z to be 0, you do end up with an ellipse in the xy plane. So you get an elliptical cross-section in the xy plane. But let's suppose you make z equal to 0, then you get a hyperbola in the yz plane, opening out around the y-axis since the y is positive. If you make z constant and non-zero, you can move this term to the other side. That's just going to increase the radius of the circle in the plane parallel to the xy plane, or the size of the ellipse, rather. So we get a curve shaped like this, a hyperboloid of one sheet. These look very much like a venturi. Old carbureted vehicles had an inlet that had a narrowing. As air went in, you have the same volume per minute of air passing this point as you do this point, which means that it has to be going faster to fit through this narrower passage. That's the place in the carburetor where you inject the fuel. In that way, the fuel is ripped apart and atomized and made as much of a gas as possible before entering the cylinders in the engine. As an example, let's suppose we have x squared plus y squared minus z squared equals 1. We have then a circle of radius 1 in the xy plane. The hyperbola will open around the z-axis, of course. If you wanted to, you could put a box going 1 unit in each direction to draw in the asymptotes. The surface will go asymptotic to these lines in particular directions, and that gives you this hyperboloid of one sheet. Third, if there's a hyperboloid of one sheet, I suppose there might be a hyperboloid of two sheets, but don't go 3 sheets into the wind. These are of the form x squared over a squared minus y squared over b squared minus z squared over c squared equals a positive 1. Now we have 2 negatives for the hyperboloid of 2 sheets. It doesn't particularly matter where you put those 2 negatives, only that there is 2. If you have one term that is positive, there will be an axis down that coordinate axis. You'll end up with something that notice that if x is equal to 0, you have 2 negative terms equal to something positive. That's not possible. So you get nothing around the origin. Nothing at all in the YZ plane. In fact, you have to get x to be big enough to overcome the negative values to get anything at all. Note that if we can rearrange this to be x squared over a squared minus 1 equals y squared over b squared plus z squared over c squared. You can only get points on the graph when a is at least a or less than minus a. In between, you get nothing because there we'll have something negative here and something positive. X has to be bigger in order to get something positive here. If x is positive, you end up with an elliptical cross-section parallel to the YZ plane. So you'll end up with something elliptical out here. But the farther you go out, the greater the size of that ellipse. So you'll end up with something elliptical parallel to the YZ plane, and then if you take Z and make it equal to 0 in parallel to the XZ plane, then you'll have hyperbolas. So you end up with hyperbolas going in cross sections that go through the x-axis, but parallel to the YZ plane, you end up with elliptical cross sections. So you end up with these little cups facing out along the x-axis for this hyperboloid of two sheets. I'll produce something on my computer as a graphic that might help you later. 4. Suppose we have x squared plus y squared minus z squared equals 0. Not 1 this time. If it were a 1, we would have a hyperboloid of one sheet, but now it's 0. How does that affect things? This is called a cone. If we divide by a squared, b squared, and c squared, we get what is called an elliptic cone. As an example, let's look at x squared plus y squared minus z squared equal to 0. You can clearly move the z squared to the other side, and then for each fixed z, you end up with a circle in this case, more generally ellipses, with the radius increasing linearly with z. So you get a cone. It actually has two parts. Z could be positive or z could be negative. We have an upper nap. Is that a new word for you? We also have a lower nap. If you chop the cone off, you get what is called a frustum of a cone. We've done 4 quadric surfaces. There are 2 more that we need to classify. The next surface has terms that look generally as follows. Notice that one variable, it doesn't have to be z, must have highest degree equal to 1, and the other 2 variables highest degree equal to 2. In that case, you get what is called an elliptic paraboloid. If I have, for instance, z equals x squared plus y squared, notice that if z is equal to 0, x and y must be 0. So it goes through the origin of the R3 coordinate system. For z values that are negative, you get nothing, because you can't have a negative equaling something positive. So you get nothing in the lower half space. In the upper half space, where z's are positive, for each fixed z, you get a circle of radius square root of z. So the size of those circles will grow in a square root-like fashion, and you end up with an elliptic paraboloid. Now, this particular elliptic paraboloid is a surface of rotation as well. They don't all have to be, because they don't have to have circular cross-sections. They can have elliptical cross-sections. When they have circular cross-sections, they have interesting reflective properties. In particular, this is the basis, this shape is the basis for all satellite dishes, reflecting telescopes, and the like. For instance, if you have a circular elliptic paraboloid, then let's suppose you have a mirrored surface in this shape. Light rays coming in will bounce and all head towards a particular focus. And so light rays coming in will collect at the focus, and you'll typically have some kind of a mirror there which reflects to an eyepiece, and that allows you then to look and see this amplified light image from light coming from a distance. The idea being that you're taking light from a big circle and compressing it into a small circle, focusing it into that smaller realm. That increases the light intensity from these distant objects that is reaching your eye, changing the size of your pupils effectively from tiny to as big as your telescope gets. The telescope is usually described by the diameter. So a 10-inch telescope will have a 10-inch diameter on the reflector. A 100-inch telescope will have a 100-inch diameter on the telescope, etc. So one of the main problems in astronomy is not that objects are too small because they're far away. That's usually not the problem. The problem is usually that they're so far away they're so dim. Remember, as light, as an object is moved twice the distance away, the light intensity is 1/4 as great. So each doubling of the distances changes the light intensity by 1/4. There's an inverse square principle on light intensity. So objects that are very far away, say several million light years away, are going to be quite dim. In fact, the great Andromeda galaxy has a diameter of about the size of the moon, but it's so far away, it is very dim. It's difficult to see. However, it is possible to see sometimes with the naked eye if you know where to look and if you are in a place far away from terrestrial sources of light, far away from a big city. If you drive way out in the middle of a dark country night, you can look up in the winter at the just under Cassiopeia, you'll see the Andromeda constellation, and in that constellation there's a fuzzy dot. That fuzzy spot is several hundred billion stars called the Andromeda galaxy. With a pair of binoculars, you can usually see the Andromeda galaxy during the winter, especially even if you are near a city with a lot of light pollution, a lot of light sources that otherwise would obscure the view. A pair of binoculars usually allows you to see the Andromeda galaxy as a fuzzy cotton ball-like smudge in the night sky. Headlights work in reverse. You have a light source going out, hitting the mirrored surface and forming a beam going out in front of an automobile. They have a paraboloidal shape reflector in headlights. At the Houston Museum of Natural Science, or the Natural Science Museum at Tampa, and a number of other places, you'll find these little paraboloidal dishes having a little place set up for you to put your ear or your mouth, and someone whispering into this piece, despite whatever noises may be around them, whether it be people or wind or whatever it may be, cars. The person with their ear over here will receive those sound waves and have them concentrated in such a way it almost sounds like the person is speaking inside of your head. Our next surface is similar to the elliptic paraboloid. The difference being this minus right here. And again, whichever term is degree 1, doesn't matter which variable it is, and it doesn't matter which one of these gets a plus and which one gets a minus, just that one get a plus and one get a minus. This will give you what is called a hyperbolic paraboloid. So for example, if we hold z to be equal to something like 1, now how are we going to graph this thing? Note that if y is equal to 0, you end up with a parabola going up in the xz plane. And if x is equal to 0, you end up with a parabola going down in the other direction. If z is held constant, say z equals 1, you end up with a hyperbola going like this. Either way, what you end up with is called an hyperbolic paraboloid. For each change in x, it's a vertical translation on the z-axis for the parabola going the other way. So you end up with something that looks like a saddle. A good way to draw these is as follows. Something like a saddle. It's very important that you understand the hyperbolic paraboloid and the elliptic paraboloid. An understanding of these surfaces will be essential for our understanding of extrema on surfaces later. So we've now gone over all 6 kinds of quadric surfaces. You can imagine what I'm going to do in the exam. I'll give you 6 equations representing quadric surfaces, and I'll ask you to do 2 things. I'll ask you to identify it in terms of one of these 6 types, and I'll ask you to graph it. Here's an example. Suppose I have 3x squared minus 4, y squared plus 12, z squared minus 12 equals 0. What kind is it, and how do we graph it? To set this into its standard form, we'll have to move the 12 over, and we need these to equal 1 if possible, or 0. Since we can divide both sides by 12, we'll have x squared over 4 minus y squared over 3 plus z squared over 1, if you will, equals 1 after we move the 12 over and then divide both sides by 12. When we cancel, we get this. You can see we have 1 minus sign. That makes this a hyperboloid of 1 sheet. It opens around the y-axis. A little bit bigger on the x than on the y, a little bit squished this way. So something like that. If I give you x squared minus y squared minus 9z squared equals 0, what is it? Well, you can move these negative terms over. If you move all the terms over, you'll get negative x squared plus y squared plus 9z squared equals 0. The equals 0 part tells you you're dealing with a cone. It's going to open around the x-axis. It's perhaps better to write it as x squared equals y squared plus 9z squared. You'll have ellipses parallel to the yz plane, and they will get bigger and bigger as x goes out. You get kind of squished ellipses parallel to the yz plane, but this will go through the origin, so it's going to be a cone. Something like this. It's called an elliptic cone. Identification is an important part of this process. You're going to have to be meticulous in attention to the details. Equaling 0 here is a clear indication that you're dealing with a cone, and not a hyperboloid of 1 or 2 sheets. Suppose I have 2x squared plus y squared plus z squared plus 4x minus 4y plus 2z plus 3 equals 0. You might guess, since all of the coefficients of the quadratic terms are positive, that this is an ellipsoid. Well, it's either an ellipsoid or a degenerate case. So let's try to figure out which is which by grouping the like terms. For the quadratics, we need to factor out the coefficient of the x squared if possible. Leave a gap, because we have to complete squares next. We'll have y squared minus 4y, leave a gap. Z squared plus 2z, leave a gap. And move that 3 on over to the other side, giving you a negative 3 here. When completing the square, you divide the coefficient of the linear term by 2 and square it, and that's what you need to add in these blank spots. So we need to add a 1 here. That adds a 1 to the other side as well. In the second grouping, if we divide the linear term by 2 and square, we need to add a positive 4. Negative 4 divided by 2 is negative 2, squared is positive 4. That adds a 4 to the other side. In the first grouping, 2 divided by 2 is 1, squared is 1, but it's weighted with a factor of 2. So we add 2 to the other side. So that gives us 2 times x plus 1 quantity squared plus y minus 2 quantity squared plus z plus 1 quantity squared equals 4, 5, 6, 7 minus 3 is 4. If you divide everything in sight by 4, you will in fact get the 1 on the right hand side that we're looking for. It opens out square root of 2 in the x direction, plus or minus, 2 in the y, and 2 in the z. With the center of the ellipsoid, definitely an ellipsoid now, not a degenerate case, the center of the ellipsoid will be at -1 to -1. I wanted to show you how to graph these things in a computer algebra system called Maple. I'll use the plot3d command, and there are a number of different ways of doing this. I'll show you first. If I have, say, x squared divided by 25 plus y squared divided by 9 plus z squared divided by, let's say, 4 equals 1. This should be an implicit plot. Oops. We're going to go from -5 to 5. You have to use scaling equals constrained. Oops, I forgot to specify the range of the z variable. And I give you an ellipsoid. It is kind of tic-tac shaped, isn't it? We can improve the appearance, since it's only plotting a few points, by changing the number of points that's being plotted. Usually 1,000 makes it better. 10,000, better still. And here you have the ellipsoid. We can add axes by right-clicking and adding normal axes to this. And then that allows you to see the cross-sections projected onto the various axes from various angles. An ellipsoid. Now, let's change just one thing about this. Now we have a problem. Let me change this a little bit more. you can see now we have what is called a hyperboloid of one sheet. Hyperboloid of one sheet. We have one negative in here. Let me change this a little bit more, and that makes it widen out a little bit, this little Venturi shape. If we put in the axes again, you'll have the z-axis going out through the middle. It's kind of an axis of symmetry in this case. So there you have a hyperboloid of one sheet. If we put in two negatives, we will get a hyperboloid of two sheets, and those go out along the sides with like little cups going out. Put in some normal axes. You can see there's a gap in between here along the x-axis. The YZ plane goes freely in between the two halves. This thing opens around the x-axis. That's a hyperboloid of two sheets. Now, I'm going to go back up here and change things a little bit more. We have ourselves an elliptic cone. Notice that we get this gap in the middle. That's a defect in the graphing software. If we add even more points to plot, it'll close that up a little bit more, and you can see then that this elliptic cone comes together at a single point at the origin. Now, I'm going to change it again, and we'll have ourselves an elliptic paraboloid. An elliptic paraboloid. Let me put in the axes. So you can see this thing doesn't exist in the lower half space, only in the upper half space. And it's like a mega amplifier here. You can amplify light rays or radio waves coming in, collecting at a focus on such a thing. If we change this to a minus, you end up with a saddle, a hyperbolic paraboloid. So it goes like a parabola down in one direction, parabola down in one direction, and parabola up in the other direction, right here across the saddle. You can imagine putting this on a horse and your legs going down the sides and sitting on top. That's why it's called a saddle, informally. Formally, it's a hyperbolic paraboloid. So now you've seen all 6 types drawn in a computer algebra system. The trace of a surface in a plane is the set of points of intersection of the two. So if in R3 you have a surface, maybe something like this, if you cut it with a plane, the points of intersection of the plane and the surface is called the trace. Sometimes surfaces are given as z equals a function of x and y, in which case actual points on the surface would be x, y, f of x, comma, y. If you set z equal to a constant, you get what are called level curves. So on your surface, wherever you hit z equal to constant, you get a level curve. So if z equals f of x comma y, the curves C equals f of x comma y are level curves. You can tell they're curves because this is a constraint on these two variables alone. Z is being held constant, and then whatever you choose for x, y will be determined by this equation. You only have 1 degree of wiggle room left, having assigned a constant value to z, and then this function of x and y equal to that constant. You end up with only 1 degree of wiggle room. That means you get a one-dimensional object embedded in a three-dimensional space. That's going to be a curve. Because you're setting the z equal to a constant, you have these different levels at which these curves lie. Those give you level curves. Let's do an example. Suppose you have z equals x squared plus y squared. What kind of surface is that? That is an elliptic paraboloid. Your basic elliptic paraboloid. You can see that if z is equal to 0, you get a level curve consisting of only one point. Let's plot these level curves in the xy plane. This is your z equals 0 level curve. At z equals 1, we get a circle of radius 1. Z equals 4 gives you a circle of radius 2. So this is z equals 1. Here we have z equals 4. And circle of radius 3 is at z equals 9. You get a kind of topographical map of the surface. A low point here, it goes up, 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 along the sides. If we have z equals x squared minus y squared, we have a hyperbolic paraboloid. In this case, z can be negative. If z is 0, you just get intersecting lines. Because you'll get y equals plus or minus x. If z is equal to 1, you get a hyperbola opening around the x-axis. If z is minus 1, you can rewrite that as y squared minus x squared equals 1. It's a hyperbola going around the y-axis. And the larger z is, the bigger the hyperbola is. The lower z is, the bigger the hyperbola is in the y-axis direction. So you can see the kind of saddle shape here of going down in the x-axis direction and then up, and then going the other way on the y-axis. We've spent a long time setting the stage for what we will do later on in the course. I promise you we will get to some calculus soon.